Okay, first of all, I thank the organizers for inviting me to this interesting workshop. I mean, unfortunately, because of the time difference as well as other activities here in Japan, in this area of the world, that I cannot attend many of the sessions, but I suppose that there are many interesting talks and lectures on primordial black holes. And so maybe I should not spend too much time on introduction. But anyway, let me just go directly to the inflationary model construction. There are some interesting models I've been working on. I mean, there are many hundreds of models, perhaps, for primordial black holes. But so I introduced a couple of them here, which I think are quite interesting. The first of all, but let me just mention this. This maybe already mentioned in lectures and other talks, but when the primordial block was formed, it is more sort of a, how to say, intuitively easy to understand. It is kind of formation of a closed universe in the early universe. I mean, so that's why it can sort of collapse to a black hole, form a black hole, and which can be seen as because of the they say non-trivial positive curvature, local spatial curvature, which is positive, and which leads to the collapsing universe. And so so this is kind of the formulation. I mean, you consider sort of what is called spatial gradient expansion, or separate universe approach, and you just focus on one single, say, local horizon patch, and you may have some non-trivial spatial curvature if it is positive, and if when the universe expands and the size of this positive curvature region becomes of order of the Hubble size, and if it is of the same order of the Hubble parameter, then the universe starts collapse, as in the standard sort of a closed Friedmann universe, in the radiation-dominated universe. So in that sense, but actually this, if you, since the primordial black hole form at the horizon scale, in this sense, if you evaluate this curvature at the horizon crossing, then scale, then essentially it is equal to the density perturbation. So that's why I mean, seeing this as the collapsing matter is equivalently okay, but from, if you start from very early universe and the evolution of those perturbations, then it's more better to sort of intuitively better to think this as the collapse is due to a positive curvature of the space. Anyway, because of this, and because essentially the horizon size collapses, and it's like a closed universe, you could easily imagine that the spin of primordial black will be very small. And actually, in these last few years, that there are some analysis which tells us that the spins are indeed small. So this is one very important sort of a prediction of a primordial black hole scenario. I mean, which originated from curvature perturbation, say from inflation. Okay, and the one first model I would like to talk on is the sort of what we call Scalaron+x or chi model. Essentially, the Scalaron model is so-called Stravinsky model, the R plus R square model, which seems to be one of the best models to explain the large-scale cosmological perturbations, CMB, anisotropy, and so on. So we just take this as a background model, and you just add some additional field chi, and you assume that actually towards the end of inflation, maybe 20, 30 folds before the end of inflation, this chi field start to dominate, and so you have essentially two-stage inflation. In this case, when this is the first stage inflation, and then at the end of the first stage, there is a sort of fast rolling and overshooting of this field, and before it start rolling towards the sky direction. And this fast rolling and overshoot, this oscillatory frequency is fixed by the mass of this phi field on this direction. So this mass, if mass is much greater than the Hubble scale at the after of the second stage, then you have a very, very sharp turn. And this very, very sharp turn produces a very sharp peak in the spectrum. And this sharp peak can give rise to almost monochromatic mass function of black holes. And the reason is that well, in this model, in this specific model, we find that the non-Gaussian is very small. So essentially, the sort of mass function of black hole depends essentially on the exponential minus the critical sort of a threshold for the black hole formation. This is order 1 divided by the power spectrum. And the power spectrum is small, much smaller than 1, then this exponential factor is huge. So this means that if you have a peak in P, which becomes order 1, or it's not order 1, 0.01 or something, and in the remaining part is very, very small, then you have essentially a spiky mass function. So this model can produce a monochromatic primordial black hole mass spectrum, and it actually can be a cold dark matter of the universe. Okay, and so next model is a very recent model I studied with this many people from China, and this is Jihan Zhou is the student. Actually, he's an undergrad student. He's very, very good, and he has done most of the analysis. Anyway, in this model, we sort of assume kind of an action monodromy type potential, oscillating potential, as shown here. But assuming that the amplitude of the oscillation becomes larger towards the end of inflation, then at certain moment, the barrier becomes of this oscillation becomes so large that the evolution towards the phi direction stops. And then again, you add some extra chi field, let's say, then the universe starts to roll down towards chi direction. In this case, because of the small oscillations, if you consider the fluctuations in this scalar field phi, this will be amplified by this oscillatory potential, just like this amplification in the Matthew equation. But after the phi field stops at this the barrier, and then because all the background field just decays out because it becomes massive, and accordingly delta phi also dies out. So in the end, this is the original sort of amplified scalar field will not contribute to the curvature perturbation of the universe, while because there is a coupling, always because of this non-trivial potential, you always have some coupling between phi and chi, and through this coupling, the fluctuation delta phi actually induces the fluctuation delta chi, and this field is almost massless, or it is very, very small mass, and it plays a role of the infrared and the second stage. This can be enhanced and becomes a constant on superhorizon scale. Therefore, this delta chi actually leads to a huge enhancement in the curvature perturbation. So, although originally delta phi is enhanced, the final curvature perturbation is controlled by the amplitude of delta chi. But delta phi plays a very important thing later in this gravitational wave context. I will come back to soon. Anyway, as for the curvature perturbation spectrum, so you have some huge enhancement like this. So this is one typical example that the enhancement factor is like 10 to minus a million times greater. So that originally the amplitude is like 10 to minus 8 those cosmological curvature perturbation power spectrum, but it can be amplified to about 0.01 or so and this can give rise to abundant primordial black hole formation. So, this is another model which can which can give rise to lots of primordial black holes, and can also account for, say, cold dark matter as well. Now, how about gravitational waves? There are two components of gravitational waves. The one is this sort of induced gravitational wave from the curvature perturbation, which I will talk about later. But here, the most important contribution comes from the gravitational wave generated during inflation. This is because delta phi, now which didn't in the end contribute to the curvature perturbation, can be amplified. This fluctuation, when it is amplified, can give rise to a gravitational wave generation during inflation, during when these fields are within the horizon. So, and so this gives essentially, and the for this parameters which gives rise to this a large abundant primordial black hole, we find actually the curvature perturbation, the gravitational wave generated from during the inflationary stage actually is much greater than the standard sort of induced gravitational wave from the curvature perturbation. And for example, in this case, we have this LISA sensitivity curve, and it can be, I don't know how many order of magnitudes, like 3 or 4 or 5 order of magnitudes greater than this LISA sensitivity. So this can be easily tested by LISA. Well, it takes another 10, 15 years though. Anyway, so this means that this model has an interesting property that the delta chi relates to primordial black holes. Therefore, you can probe this model by if we find this mass function of primordial black holes, can be used to probe the feature of delta chi, while gravitational waves experiment, say by LISA, will tell us about the feature of delta phi. Okay, and the third model, which is a more sort of a, how to say, brave kind of model, is that the something like the primordial black hole explains everything. So primordial black as MVP of the cosmology. So this is based on the say primordial black formation during inflation due to vacuum tunneling. If you have some some kind of slow rolling sort of a again, this is a two-field model. So the model with one direction, they have some non-trivial sort of barrier, and then may have some a lower minimum of the potential. Then during inflation, there's a probability, and depending on how you configure this barrier, that the probability of tunneling from this inflaton trajectory to this a false vacuum, say it's in some sense with quotation true vacuum minimum. However, as the inflation proceeds and the energy density, the vacuum density decrease and becomes smaller than this bubble, which is formed formed due to the tunneling, then this higher density vacuum region will become a black hole. And so that's why this kind of a quantum tunneling during inflation can lead to primordial black hole formation. And this, in some sense, means that if there are many tunneling in many directions, you may be able to test some kind of multiverse scenario. Anyway, the important point is that now if you sort of boldly assume that actually you have some so the sort of nominal kind of or the default sort of spectral would be that you have some cutoff on the short small mass scale, and this primordial black hole spectrum behaves like m to the -1/2. However, if there are some intermediate matter dominant stage after inflation, maybe due to some other massive particles and so on and so forth, and which decays later, then this spectrum is deformed, and you will have some a constant sort of a amplitude spectrum. And then so this can be just configured. You have the freedom of this choice of when the black universe enters matter dominant stage and when it ends, and so on. So then, for example, if for this matter dominant stage, the spectrum becomes flat, and then after, in the end, that the universe has to become radiation dominated again, and it start decreased. Oops. So in this kind of case, you see that essentially you can find you can explain the cold dark matter by these small scale mass primal black holes, and you may be able to explain this LIGO, Virgo, those black holes of 10 solar mass, 100 solar mass black holes by say the scales of M2, and maybe for very, very large mass scale, you still have this M to the -1/2 spectrum, which may account for a seed for supermassive black holes. So this is a very, very bold conjecture, but in any case, it may be able to explain almost everything we need to explain. And in another very observational, very interesting thing is that if this is indeed the case, actually there's a very good chance that the very recent Subaru Hyperspring telescope can test this model within a few years, and actually, so this proposal of the observation is already accepted, and it is ongoing. And we hope that we'll have the result. I mean, result, we do need lots of analysis, but oh, by the way, this is by this gravitational lensing, micro lensing. So analysis may take a year or so, but in any case, within a year, a couple of years, we will have some interesting result and may find some evidence of a primordial black hole. Okay, now let me just talk about this large curvature, the gravitational wave generated from large curvature perturbations. I guess probably many people have already discussed this, but let me just go through quickly. So as I said, that the curvature perturbation in the early universe, if it is large enough, and then it can sort of collapse to a black hole. So as I said, it's like forming a closed universe in our universe. While if the amplitude is not so large, if it is during the radiation dominance, of course, it start oscillates, and this means that you have some, of course, from local point of view, a non-trivial time variation of the quadrupole moment, or it's just a time-dependent oscillatory behavior. It's dynamical space-time can produce gravitational waves. Therefore, and this will produce some a gravitational wave, and so this means that if you have some spectrum of the curvature perturbation, say generated from inflation, then at least some part, of course, this may be very, very, very small fraction, but some part where the curvature perturbation is large will form a black hole, and others leads to gravitational waves. And interestingly, in this model, that the primordial black holes are cold dark matter with the mass of say 10 to 21 gram, or more or less about this range. The corresponding frequency of the gravitational wave is in the LISA range, and that's why, I mean, the background, this cold dark matter scenario actually equals primordial black holes can be tested by LISA. Unfortunately, for the current sort of LIGO Virgo sort of range, which is about 100 hertz, this frequency is relatively too high. So, of course, this might have some very interesting implications if we find some non-trivial cosmological background. but it is not directly related to this model. Okay,
So we have about 4 minutes.
Okay, sorry. Yeah. Yes, I should hurry up. Anyway, so this is already actually this the spectrum of the gravitational wave produced from this large curvature perturbation has been already computed more than 10 years ago, decade years ago, this Saito and Yokoyama, and so we can just directly use the result. And you find that actually, as I said, it just crosses LISA or maybe the SIGO BBO bands. So this is a very, very interesting implication. And recently we have also considered the case of non-Gaussianity, and by using this sort of a standard FNL parameter, see if a non-Gaussianity can change all these results. And interestingly, that even if you get very, very high non-Gaussianity, it does reduce the amplitude of the gravitational wave, because the this means that the relative sort of amplitude must be small. The non-Gaussianity in the tail can produce a large amount of black holes. So this means that the amplitude must decrease. But still, if energy becomes very large, the power spectrum from this non-Gaussian part becomes dominant, and this will keep contributing to the gravitational waves. And in the end, even for very, very large non-Gaussianity, the amplitude of this gravitational wave will be larger than the LISA sensitivity if you assume black holes are cold dark matter. Okay, I don't have time to go through this binary black hole case, so let me just skip and go to the end and summarize my talk. So essentially, there are many interesting probably models which produce primary black holes, but most simply, if you just introduce one more field, two-field inflation model can produce abundant primary black holes, and they can also produce a lot of gravitational waves. And if you assume that the cold dark matter is dominated by primary black holes with this fairly small mass range, 10 to 20 gram or so, then induced gravitational wave must be detectable by LISA, independent of non-Gaussianity. And so conversely, if ESA within a couple of decades, if LISA doesn't detect anything, any gravitational background from the early universe, then it constrains primordial black hole abundance severely. Another thing is that I talked about this resonant amplification model, and in this case, the gravitational generated during inflation can dominate, and in this model, primordial black holes gravitational waves essentially gives complementary information about the two-field model. Primary black hole from vacuum tunnel during inflation may explain everything. This is the most bold conjecture, but it's a very exciting, and it can be actually, we will have some test within a couple of years. And then finally, this Raghavan black hole may be primary black holes. This I didn't have time to talk, so I stop here. Thank you very much.
Thank you very much, Professor Sasaki. You, in fact, finished earlier also. But we could take some time for questions. Yeah. So we do have so many interesting questions. So first question is from Patrick Dasgupta. So he's asking, in the spiked mass spectrum in which the primordial black hole's mass peak around 10 to the power 20 grams, one should be able to constrain the abundance by looking at soft X-rays and UV coming from Hawking evaporation. What do you think?
Wait a minute. So you are talking about this?
Yeah.
Well, yeah. Actually, this how to say this line, it comes from this black hole evaporation constraint, and so as this assumes standard sort of a Hawking radiation, and you do have some constraint up to maybe 10 to 16 gram or something, but beyond that 16 and 17. So at least within the range of, say, 10 to 20 gram or so, you actually don't have any constraints from evaporating black holes. Yeah.
Okay, yeah, thank you. Patrick, if you have any comments on this, you can type the question, type it back. Another question is from Juan Garcia Bellido. If the gravitational background from the resonant production occurs 20 e-folds before the end of inflation, why isn't it redshifted by the inflation?
So sorry.
Is the gravitational background from the resonant production occurs 20 e-folds before the end of inflation, right? Why isn't it redshifted by the inflation?
Oh, yeah. No. So of course, I mean, so how should I say? They will be. You have some amplitude, and then when it comes out of the horizon, it's exactly the standard as the case of standard vacuum fluctuation. The amplitude will be frozen because it's massless. Yeah. So it behaves exactly like the vacuum say gravitational wave from the inflation, except that the amplitude is exponentially enhanced.
Okay. So another question is from Rajiv Kumar Jain, and he's asking, can one see an imprint of a locally closed universe in the induced gravitational wave background?
Oh, you mean that the say essentially from this maybe some effect from near the black hole, near primordial black holes? Is that the question?
Is that what you mean, Rajiv?
Well, as I said, well, I'm not exactly sure what the question is. Let me see. For example, yeah, I draw this kind of graph. Yes. So this is essentially from outside. It's essentially standard black hole. But if you're inside, yes, you're part of me. You may, and if it lives long enough, then it may be kind of part of a closed universe. Yeah. I don't know. So is that the answer to this question?
I guess. Okay, yes, he's answering yes. Okay, last question is from Christian Bynes. Since he's the next speaker also, I would ask him to ask the question directly. Dr. Bynes?
Sure.
Chris?
Hi, Misao. Yep.
Hello.
I was thinking about the Starobinsky model. I thought it was a sort of so-called attractor model where the spectral index is something like -2 over the number of e-foldings. Now, if half of the e-foldings are generated by the other field, the chi field, won't the spectral index become twice?
Oh, yeah, that's right. Actually, so actually in this paper we have mentioned that if we just strictly just focus on this model, then the spectrum index would shift towards the even the red side. Right. And it cannot be it cannot explain cosmological perturbations. I mean, now it's so sharply pinpoint at say 0.967 or something. Yeah. So we do need, in that case, if you add some very small 10 to minus 8, it was the coefficient of 10 to minus 5 r to the cube term. So some small correction. Yeah. Then that can explain that can sort of bring back this spectrum index. So we think, I mean, this is just to so it doesn't have to be Scalaron, but another interesting thing is that if you do have this kind of sort of a scalar model from say curvature, higher order curvature, then by going to Einstein a frame, you will have non-trivial sort of kinetic terms and everything on this the other fields, and in this specific model, this didn't play too much role, but except that it does add to these oscillations, but it can actually play very interesting roles. For example, the modulating some these fluctuations in chi and so on and so forth. So. So that's why one of the other reasons that we sort of like this kind of curvature model, but other models can do the things as well. Yes.
Okay, thank you.
Okay, maybe you can take the last question, which is a follow-up of this question on the background from the Hawking radiation from evaporating black holes. So Patrick is asking, even higher masses like 10 to the 20, can one expect a UV background, even if you cannot expect a gamma ray background?
Maybe. Well, like, I think yes. I think there has been some papers on this topic, and I don't exactly recall, but I am pretty sure that they find it was not a crucial. I mean, so that's the reason why we don't have this kind of constraints. Yes, it is true that yes, even if for some fairly large mass, I mean, it's sort of because it depends on 1 over m to the cube. I mean, the emission temperature becomes very, very small, but still, yes, if maybe yeah, if you just was it the 10 to 20 gram, and when the temperature will be on the UV background range, maybe
that's what Patrick calculated.
Yeah. Maybe yes, but yes, I think that the say the density or the say how to say the luminosity, whatever you call this, of this UV will be small enough to be allowed.
Okay, thank you very much for this very interesting talk, Professor Sasaki.